So my name is Eric. I don't have two microphones, I hope not. This is Functional Programming in Plain Terms. I tried to think of a joke title for this talk, and then I realized that that would probably defeat the purpose of it, but then I saw Aaron's closing keynote, and I was like, maybe I'll call it like FPPT, but then I kept saying FTTP, so I'm going to stick with the theme of being simple. Before we start, I tend to talk really fast, especially when I'm excited, which is the case where I get to talk to all of you about things like Monads, which are intrinsically exciting. I'm sure you agree. But also the first time that I'm able to see you all in person at RailsConf in 3 years. This is also the first talk I've given in 3 years, so I'm super nervous. So I'll probably start to talk faster. If you start missing words or I'm going like really off the rails, feel free to like wave or just make a commotion. Yeah, exactly, big commotion. But exactly like that, get my attention and like slow down or some kind of inventive hand signal for me to be louder or talk more slowly. And then just thank you all so much for being here. I know you have lots and lots of places you could be. I really appreciate your spending your time here with me. Thank you also to our amazing sponsors, obviously to the RailsConf organizers and to the city of Portland. So a bit about me. I work at a company called HashiCorp. Some of you, hands, who's familiar with HashiCorp? And okay, cool. I won't give the whole spiel, but I work on the Terraform Cloud side of things on a brand new team called Infrastructure Lifecycle Management, or ILM. I like to pretend that it stands for Industrial Light and Magic, but ILM is Infrastructure Lifecycle, really attending to the lifecycle of terraformed objects. So lots of cool stuff coming down the pike, some cool stuff that we'll be announcing at HashiConf EU and HashiConf. We are hiring, so if you'd like to talk to me, please feel free. Up here you also see my GitHub, Twitter. I tend to be Eric Q. Weinstein. I joke that the Q stands for QUEUE. It doesn't, it stands for Quinn, but it's just like all I'm made of now is like bad programmer dad jokes. There's this book, Ruby Wizardry, that I wrote about 7.5 years ago. Normally there's a discount code. I didn't apply it this time because I don't want to urge you to buy a book that's like 8 years out of date. I will at some point talk to my publisher. Maybe we'll do an update for Ruby 3.1. I'll keep you all posted, but if this is interesting or you want to talk about this book or you'd like a copy, please do come see me after the show. All right, it also occurs to me that I have this now, so I can be more free in my walking around. So it's not a long talk, but I figure we benefit from an agenda. So what we'll be talking about today is context and developing intuition and kind of peeling away the sort of forbidding language around functional programming, explaining what it is and how it works, and then giving you like a dose of the real vocabulary so you can Google things and stuff like that, but really focusing on what things like pure functions are, algebraic data types, functors, monoids, monads, and then tying it all together with some Ruby examples. There's a little bit of Haskell, but I promise it's not imposing. So why this talk, right? This is meant to be like a cleansing talk to kind of be the antidote maybe to prior frustrations or to build a bridge for you if you felt like you've almost gotten these concepts or you feel like they're really interesting, but it hasn't clicked for you. It's also meant to provide some motivation, why things like pure functions are helpful, develop some intuition, and give you some translations from like functional programmer-ese into Ruby. Like I said, so you can Google the actual vocabulary, but you can have these conversations with functional programmers, but ultimately, showing how this works for Ruby and Rails and for you, and not saying, hey, you have to go to Haskell or Elixir or Clojure. You can borrow these ideas, you can participate in those communities, but all of these things are available to you in Ruby, which I think is really cool. And I think naming things is tough, right? A quick aside, I was terrible at dynamic programming for a long time. I'm still not super good at it, but I wish someone early on had said, think of it as loop table programming. Or, as one of my best friends in the world calls it, programming with a cache. And I'm like, oh, that makes way more sense. Why don't we just call it that? Actually, that one was deliberately obfuscated for funny historical reasons. But anyway, all this to say, functional programming is not arcane necessarily. Functional programmers are not necessarily smarter. It's just a different set of abstractions and the way of thinking about things. And I would urge you to really focus on what is this for? I think it's a really compelling question. It's like the yin-yang sort of like, what are you trying to do? What is this for? And what is this for, I think, gets you better answers than what does this do or what is this? What is this will get you a definition. What is this for will show you its utility. And so as we explore these ideas, we're going to look at the constraints of a language like Haskell, which only has pure functions. Everything is either an input to or output from a function. So understanding those constraints and why it is the way it is. And I'll probably use an analogy here and there where it's kind of like, imagine there's an imaginary C programmer at your elbow while you're writing Ruby, being like, whoa, you're not managing the memory yourself? Like, what kind of madness is this, right? And then try to develop that sort of intuition around how someone who is used to having Haskell or Elm manage those kind of side effects for them and say, whoa, things can be nil, state can be mutated. Is this madness, right? So try to keep that imaginary C programmer in your mind, and that will, I think, give you a good sense of what we're trying to aim for by having these constructs. Is this pace good, by the way? Too fast, too slow? Excellent, thank you. Okay, so pure functions. Pure functions are functions that just can be memoized, which really just means you could replace the function call everywhere in your program with the value it returns, and your program still works all the time. This would not be true for something like if you're writing to a log file, if you're updating the database, if you're making a call over the network, where sort of this spooky action at a distance can occur. Those functions cannot be memoized. They can't be replaced with their return values because they have side effects. So side effects are things like doing I/O, doing state mutation, things like that. These things are not bad. Side effects are in fact critical because without them, your program would not do anything. It would, I guess, keep the processor, and by extension you, if you had enough of them, warm, but you couldn't even print to the screen without side effects. And so they are necessary for useful programs. And so the idea here is to use things like pure functions, to use things like immutability, where you don't update a value, you just are returned a brand new one, because it makes it easier to reason about your programs. You can see exactly how things are going to change. You get things like idempotence, like you can do the same thing over and over, and the result doesn't change. And you can just get to that sort of north star of sort of safe concurrency. So I think that's one thing to keep in mind, is safe concurrency, especially in the age of multi-core, many processors, is pretty key. So having talked about that, there's a little bit of legwork we'll need for our first topic, which is algebraic data types. So we're going to look at a quick crash course in Haskell types. Haskell's syntax is very bare, it's very minimalistic, which is why it is so confusing. So we'll walk through this one real quick. If you're not familiar with Haskell, this is a function just called add, : you can read as has type. So the idea here is you have a function called add. It takes an integer and another integer and returns an integer. An interesting thing about Haskell is that all functions are sort of curried by default. No need to worry about that if that's not a thing you're familiar with, but the idea is you can sort of read the type signature as everything except for the last thing are arguments, and the last thing is the return value. And then that second line is the actual implementation. This function is called add. It takes an x and a y, and it is equal to, it is defined as x plus y. So again, just very, very bare bones, but this kind of type, even just using Haskell type signatures in Ruby or in Elixir or other languages, I found really valuable to think about types. RBS, I think, is a great start, but one thing that I find really compelling about Haskell's type system is that eventually, and this is true, I think, of Elm as well, and other MLs, you get to a point where you can almost program in your head. You have these like little Lego bricks of type signatures. And there's actually a phenomenal book by Edwin Brady. It's about the language Idris, which is very similar to Haskell, called Type-Driven Development. And it is exactly that. You kind of figure out what your types are, and you kind of dial those in. And the nice thing is, because the compiler will guide you when you refactor, if you eventually get a good compilation result, again, assuming you didn't add where you meant to multiply or something like that, where the type system can't help you, but you would want a good test suite to do it for you, you'll be in good shape. You can kind of fearlessly refactor, which is a great sort of thing you get for free from these kinds of powerful type systems. There's an image I was looking for, I think it's in a book I have somewhere, where it's kind of like you're trying to solve a puzzle, but like the puzzle pieces are all little squares. Like the picture's still there, but that's kind of like you're programming without a strong type system like this, and then having the types, it's like a true puzzle where things kind of click together. So that's the type system. This is a little bit more, but is going to start developing the groundwork for algebraic data types. This is a fanciful version of a function called head. So the real version of head in the prelude in Haskell will actually error. It'll throw an exception if you have an empty list. So this one is kind of a nice version that will just give you the first element of a list. And so again, we're going to say this is a function called head, : has type list of A, where A is a type variable, so it could be integer, string, anything you like. And the idea here is you have a list of A, and you get a maybe A. Not necessarily an A, but it could be an A. And the implementation below is a little bit cryptic, but the idea, this is idiomatic Haskell, which is unfortunately cryptic. The idea is if you have an empty list, so that's why there's two sort of definitions here. You kind of pattern match on what you're getting as an argument. Empty list, return nothing. This is Haskell's way of saying there's nothing here for you, but the compiler makes you say this up front and makes you check for it. So you don't have something like nil, which can surprise you at runtime. And then otherwise, if you have any elements in the list at all, the destructuring that you see in the parentheses there just says X is the first thing, colon is like the sort of cons operator, like add more stuff to the list. Underscore just says, this is not a variable that we care about because we're not using the tail of the list, we just want the head, and then return just X, just return the head of the list. So already you're seeing a more complex type, maybe A, and this is an algebraic data type, this notion of a type that is made from other types, that contains a type constructor, right? So that's what the maybe is there. So ADTs are really just types made from other types. They usually come in a couple of different flavors. One of them is a product type. If you're familiar with hashes, in Ruby they're very, very similar, but the idea is like kind of like a record or a named tuple. It's like a, like a user or a, any kind of thing where you would have fields, right? And a sum type is kind of like an enum. And the canonical example would be something like you have, you're modeling a poker game, you have the various like suits of cards, and you have like, spades and clubs and diamonds and hearts. You're only going to have those four. So you can actually model that, and the compiler will tell you at compile time if you have done something incorrect with this. So you don't have this sort of stringly typed phenomenon where you have to just kind of look at some strings and like, are these the right strings? The type system will do this for you. So here's an example that I've borrowed from Luke Plant. There's a link there for you. The idea here is this type system can actually model the results of going to the database. So you could actually have a function with a type signature such that nothing means there was nothing cached for this. I have to go to the database. Just nothing. We've done a lookup, but we got nothing. There's no record for this user, for this entity. Just nothing is we have done the search and we found something, but the field that you wanted was null. So if you're looking for a user, you're trying to look up their age, this result, this type tells you exactly that. And it's a little clunky, but just 42 is we went to the database, we found somebody, they do have an age, and it's 42. This does look a little bit cumbersome. As we get to monads later in the talk, there are ways of kind of peeling these open, kind of like getting the values out without having to do a whole bunch of boilerplate. All right. How's the pace so far? Good? Fantastic. Oh, we're right on time. I am surprised. I'm delighted. So the very first one, and I promised you the real name and what I consider to be the useful name, functors. Functors are mappables. They're things that can be mapped over. They have a name that comes from category theory. I might mention a couple category things as asides, but not critical to know the mathematics or anything like that. We'll look at the implementation of functors in Haskell, but the idea is that these are things that can be mapped over. They support a map operation. And so the list is the canonical version. The tricky thing about this stuff is that the generalizations, the abstractions, you're almost like, why would I use this? Like, isn't map like the most general thing? I have a function and I go over some collection, and it can be any function. It can be whatever I want. How can you be more general than this? So we'll see. And providing more examples to kind of knit it together for you. So this is the implementation of functor in Haskell. We're going to look at this code. The first part is the sort of definition of the type class. It's kind of the the contract, the API. Like if you, we'll walk through it, but if you implement things, in this case just the function fmap correctly, you have a functor. So class functor f_where. So we're going to define this functor class. F is going to be a variable here. And we're going to say that if you want to be functor, you have to implement fmap, which is this type signature. So fmap has type, and then a little bit confusing because we haven't seen parentheses in these types before. It's meant to disambiguate and give you, like, this is a function, right? So the first argument is a function that takes an A and returns a B, and then also takes a functor of A, which is weird, but we'll roll with it for now, and gives you a functor of B. And I think it's a little bit clearer when you look at the instance for list, where it says fmap is just defined as map. So there are many maps in Haskell. Fmap, in this case for lists, is just map. And I've put a comment down below that shows you the type signature for map, and it's just a function that takes an A and a B, and a list of A, and gives you a list of B. The compelling thing about this is this does not have to work only for lists. If you have something that implements fmap for whatever it is, these things are now mappable. So you can actually map over maybes in Haskell. There's another type that we didn't talk about called either, which models things like, did I get the result I wanted, or did I get an error? You can map over those. You can map over arbitrary data structures like trees, or like actual maps. Anything that you define, if you build an fmap for it, you can map over it. And so giving you, again, some more intuition here, this is sort of what a functor would look like in Ruby. So we've defined a quick function, or a quick method rather, square, that just takes a number and squares it. And then we say, okay, let's go over this array of 1, 2, 3, 4. We're going to map square over it. So this is the fmap for lists. This is just map. And you get 1, 4, 9, 16. I know it seems super trivial, but the idea is compelling because once you see that you can do this in Ruby and say, oh, I can like build a tree data structure, I can build some sort of active record thing, and I can kind of map over it in arbitrary ways. A lot of this has been built into enumerable, and we'll talk about that in a moment. But that's sort of the connection there, is this enumerability, this mappability exists in both languages, and you sort of get it for free in Ruby doing things like this, but knowing that you have more general options, you can do this in Haskell. And if you want to use functors in Ruby, you can get this kind of magic too. An interesting thing is that you can actually do this for functions. And just anyone want to shout it out? Does anyone happen to know what fmap for functions would be? Go for it. Exactly, compose. It's function composition. So you can map functions with, it's really that f after g after x, that kind of like pipelining is that composition there. And composition is the key to all of this. It's the most critical dimension of all the topics we're talking about in Haskell, and is honestly, I think, the key to programming effectively in Ruby. Let's talk about monoids. So monoids are accumulators. They're a generalization of accumulation. We're going to look at an example again, some Haskell, some Ruby, but the idea here is that you have a general way to say, hey, I actually have some state, like a counter that I want to increment. I have a thing I want to build up over time. This is a generalization in Haskell, and again, you'll sort of see it's almost trivial in Ruby, again, thanks to enumerable, but once you sort of see it in this light, then everything is a monoid, honestly. It's kind of amazing. So let's take a look. So again, this is a slightly modified definition. This definition of the monoid, there's actually a semigroup type class, and this is again where a lot of the category theory and mathematics, that foundation of Haskell kind of comes through. I wanted to bring this down to something that's more approachable and more programming oriented and less computer science or mathematics oriented. It's weird, you get this kind of mixture of, in math, there's lots of things that are almost exactly the same, but get extremely different names. And then in computer science, you have things that are wildly different, and they all get the same name. I think there's like 9 definitions of partition. And so it's confusing when these things mix together, but this is why we're giving these sort of human names. So monoid. Monoid actually has 2 required definitions here. So we have class monoid M, where we have M empty, which is of type M, and then M append, which takes an M and another M, and gives you a new M. It's not clear from this type signature exactly how this is meant to work, so it will be clearer when we go to the Ruby example, but this is the foundation of folds in Haskell. So here's an example from Ruby. So we might have a list, which are monoids, 1, 2, 3, 4. We can call reduce on them and say the operation we want is plus, and we get 10. So we've been able to sum up the list doing this reduction. So lists are monoids, and so M empty would be the empty list, and M append is list concatenation. You can just add stuff to the list. So we actually see this below a little bit more clearly, I think, with the hello world example, when we reduce this list of strings and we get this string back out, hello world. So if you have seen Brandon Weaver's talk on reducing enumerables, or enumerable rather, which I think was RubyConf 2018, a phenomenal talk, goes much more in depth on sort of the way that folds and enumerables and reductions all work together. But this is the same idea. It's a generalization of accumulation, and you get this for free in your Ruby and Rails applications because you have these methods on enumerable. Finally, monads, the moment we have all been waiting for. I don't know why no one seems to describe it this way. Please tweet at me if you found someone who's called monads smart pipes like a long time ago and I just missed it. But I wish someone had said to me, they're smart pipes. That's it. They're just function composers with a little bit of extra magic in them. And that's really all they are. They're not burritos, although I do know the guy who coined that, and he's a genius and I'm not, so maybe I'm missing something. But they're not burritos, they're not spacesuits, they're not They're kind of like containers, but they're a computational context. They're smart pipes. So let's break that down. So if you're familiar with the command line, the actual commands here are not important. What is important here is these little pipes, right? Unix pipes basically connect the output of one process to the input of another. And your API, when you're working in the terminal in the shell, is somewhat bare bones. You have standard in, standard out. You also have standard error. We'll ignore standard error for now. But effectively, everything is an input to or an output from a process, right? And that sounds a lot like what we were saying about Haskell, these pure functions. You can't really do, extra weird stuff. You have to just pipe whatever comes out into the next thing. And that works great in this environment where everything is, conforms to the same API. Some bytes, some text go into the next program to be processed, right? So this is an example from James Coughlin, who has written, I think, the best explanation of monads I've ever seen. This is kind of the distilled down quick version. If you have a spare hour, there's a link in the talk. You sit down, program it through. It's in JavaScript, but these examples are in Ruby. And it will really guide you through like what were the constraints and what made it so that monads were necessary, right? So again, keeping in mind we have pure functions. We can't just log things out willy-nilly. Let's say we're doing some math for some reason. So we have this lambda that has the ability to take the sign of a number, another lambda that cubes numbers. And we could write a bunch of sort of composition magic to kind of have a compose function. Luckily for lambdas, for procs, we have this sort of shovel operator. So sign of cube equals sign shovel cube. It's the same as doing sign.call and then parens cube.call and then whatever value you have. So if you call sign of cube.call 2, you'll take the sign of the cube. Fair enough. However, what if you did want to do some logging? What if you wanted to say, like, hey, we got the sign, like it happened? This is a trivial example, but you can imagine how very quickly you would want to have this functionality. The problem is now, everything has to come out of the function. It can't go anywhere else. And so you're kind of stuck. You have this kind of composite result type where you might say, do I do like a hash kind of thing, like a record? Do I do like a 2-element list? Do I do a tuple of some kind? But you need that sort of more complex type to capture the extra information. And then you would realize, sort of to your horror, that you would keep going with this process. You would have a new type signature. In Haskell, in Ruby, you would just get, there's a type error here. I can't convert an array into a float. So effectively, the input no longer maps cleanly, and you don't have that sort of nice inputs match outputs, and you can keep pipelining. So what do? Well, you could go through and write all of this boilerplate to say, okay, let me split apart this 2-tuple or this 2-element array, and then grab out the number, and then do the arithmetic, and then keep shoveling that forward. And then in this kind of like off to the side parallel pipe, I have all of the logging information accumulating and accruing. But we're programmers, so we can just abstract this away. And so this particular abstraction, this particular smart pipe that knows how to kind of like off to the side, almost like a motorcycle with a sidecar. Like the motorcycle is arithmetic, the sidecar is logging. It keeps it going alongside in this sort of smart pipe. And as long as you use that particular type of like connector, then you can basically model all of this with pure functions. And so this particular abstraction is called the writer monad and is used to do things like logging, to have some output while you're working. And this is where I think it starts to become a little bit more intuitive, because then you see the I/O monad. Oh, well, I'm going to do some I/O. That's an extra thing. That's a monad. There's a list monad. There's a monad for state, the state monad, which is kind of like that counter example we talked about. And so as you kind of go through and see, you realize that these abstractions are just trying to deal with different constraints. Everything has to be the return value from a function, which means I now need not like dumb pipes, not the almost identity monad that just kind of passes things through, but I need to bake some magic into that pipe connector, right? And I think a lot of our intuition in Ruby is the magic lives in the functions or in the methods or in the classes, and not in the pipelining itself. It's a weird place to put stuff. Like, it would be weird if you're chaining a bunch of methods and it's ... and those dots had like magic inside of them, right? But that's what monads do, and that's why they behave the way that they do. So I apologize if this is a tiny bit hard to read. This is an example from the dry monad gem, which is one of the ways that you can just do monadic computations in Ruby. So here, you may have had this kind of problem before. You go to the database, give me a user. All right, now I have a user, great. The address is the user's address. If they have an address, great. The city comes out of the address. If they have a state, et cetera, right? This is very This is very unpleasant. Using the dry Monads Ruby gem, you can now say, all right, well, I'm maybe going to get something. And then when I do, maybe there's an address. And if there is, maybe I'll get a city. And then maybe a state, maybe a name. And then at the end, you get that state name or just nothing. In this case, you replace the nothing with a no state. You want that string in this particular case. So if you are interested, you can take a look at the dry Monads gem. There's also great documentation for it. I am a big fan of kind of at least learning more about these things. Even if you don't end up using them, they are extremely valuable. So it's interesting that we talked about a lot of things, but we had to build up a little bit of intuition around types to get to algebraic data types, to kind of understand things like maybe, which is a functor, and also a monad. And we talked about functors, we talked about monoids. Functors provide that sort of compositional power, right? They give you that mappability. And again, everything is about composition. The North Star here for monads is like safe composition, like composition managing the side effects for you so you don't have to. Monoids provide that accumulation, that like, hey, stuff is happening and I want to keep track of like the value of a counter, the logs in a log file, things like that. So you have this combination of the sort of monoidal accumulation, and you have this functorial behavior. And it turns out that in Haskell, all functors are a type of functor called endofunctors, because the thing on each side of the functor is the same. It maps back to the same set, the same category. Haskell types go in, Haskell types come out. Which leads us to monads are just monoids in the category of endofunctors, which actually is, as you now have seen, smart pipes are just accumulators in the category of things you can map over. That's what that means. That's it. The original thing actually is a joke, the sort of like monads are just monoids in the category of endofunctors. That is the definition, I think, from Saunders McLean's book on category theory. I have tried to read it. It's kind of like eating a brick. So I hope that somebody produces a more like, because to be fair, it is category theory for the working mathematician. I need category theory for the lazy amateur not mathematician. So hopefully that appears at some point. Or even, I think more clearly, smart pipes are just function composers that manage side effects so you don't have to. That's all. That's all monads are. So the TL, DPA, the too long, didn't pay attention. I would say the core thing here is composition and asking, what is this for? What is this tool, this idea, this abstraction? What does it do for me? What do I get if I subscribe to this? Pure functions and immutable data structures. Pure functions have no side effects. They're easy to reason about. Nothing weird happens. You can replace them with the output of their return values and your program still works. Immutable data structures, you never have to worry about some other thread or process or thing changing things under you, because every time there's a new sort of event, you get a new value. So there's no mutation, there's just new stuff. We talked about functors, monoids, and monads. And they're just ways to solve our everyday problems under the constraint of we want pure functions because we want that safe composition. We want that sort of North Star of, oh, I don't have to worry about this. If it compiles, assuming my tests are good, it's just going to work. And finally, good type systems are amazing tools. They do give you a superpower of being able to kind of do Lego programming in your head. If this is something that you would find compelling, I recommend something like Learn You a Haskell or some of the introductory Haskell programming stuff that gives you sort of that intuition. If you're not super jazzed about Haskell, I highly recommend Elm. It is delightful. If you are one of those many, many folks here who you're like, I am a full stack, but I don't like JavaScript, I don't want to do this, Elm is a delight, so I do recommend it. So, having said that, that's all I got. Thank you so much for coming to my talk. I'm delighted to see you. Thank you.